Have you ever considered that the solid world might be woven from something smaller than a point? Imagine zooming past the stars and through the atom until you reach a layer of pure vibration. It isn't chaotic. It is a rhythmic dance of tiny, unseen threads. This is the landscape of string theory, the idea that reality isn't built from blocks, but from resonance. It suggests a hidden harmony in the fabric of space itself. Here on Fall Asleep with Science, we look for that quiet order. If exploring these fundamental patterns calms your mind, a gentle like and subscribe helps us drift further together. For now, settle in, and we'll see how far string theory can stretch our understanding of reality. Physics has a problem, and it has been keeping scientists awake at night for nearly a century. To understand this dilemma, imagine you are trying to understand a beautiful, complex song. You have two different ways of listening to it. The first method works perfectly for the high notes. It captures the delicate melodies, the quick trills, and the softest whispers. The second method is completely different. It captures the deep bass, the powerful rhythms, and the way the music fills the room. On their own, both methods work wonderfully. But when you try to use them together to understand the complete song, they give you completely different answers. They contradict each other. This is essentially the predicament modern physics finds itself in. We have two incredibly successful theories about how the universe works, but they are like oil and water. They simply refuse to mix. The first theory is called quantum mechanics. It describes the behavior of the smallest things in the universe with stunning accuracy. Atoms, electrons, photons, and all the tiny building blocks of reality dance to quantum rules. These rules are strange and wonderful. In this world, particles can be in multiple places at once. They can tunnel through barriers that should be impossible to cross. They can be connected across vast distances in ways that seem almost magical. Quantum mechanics is not just theory. It is the basis of our modern technology. It has given us computers, lasers, MRI machines, and smartphones. It works so well that some of its predictions have been confirmed to more than 10 decimal places. The second theory is Einstein's general relativity. This theory governs the large-scale structure of the universe. Gravity, space, time, black holes, and the expansion of the cosmos all fall under relativity's elegant mathematical umbrella. It tells us that massive objects warp the fabric of space-time itself. It proposes that gravity is not a force pulling on objects, but the result of objects following curved paths through bent space. General relativity is also a triumph. It predicted the existence of black holes decades before astronomers found them. It explained the strange orbit of Mercury and told us the universe was expanding long before telescopes confirmed it. Both theories are masterpieces of human understanding. But here is the problem. When physicists try to apply both theories to the same situation, the mathematics breaks down completely. It is not just that they disagree, it is that they produce infinite, meaningless answers. Imagine asking two friends what time it is. One says 3 o'clock, while the other starts reciting the entire works of Shakespeare backward. That is roughly the level of confusion we are dealing with. This becomes particularly troublesome when we try to understand situations where both quantum mechanics and general relativity should apply. Think about the interior of a black hole, or the very first moments after the Big Bang. These are places where the universe is both incredibly small, meaning quantum effects matter, and incredibly massive, meaning gravity dominates. Our current theories simply cannot handle these extreme conditions together. And so, Physicists have been searching for what they call a theory of everything. They are looking for a single framework that could describe all the forces of nature, from the quantum to the cosmic. It would be like finding a universal language that could describe both the whisper of an electron and the roar of a black hole. It would unite the delicate quantum dance inside atoms with the grand waltz of galaxies through space. String theory is one of the most promising candidates for this theory of everything. It is an idea so radical, so mathematically complex, and so far removed from everyday experience that it sounds more like science fiction than science. But it might just be the key to understanding why the universe works the way it does. The basic idea is both simple and profound. It asks a fundamental question. What if all the particles we think of as fundamental electrons, quarks, photons, are not actually fundamental at all? What if they are all made of something even more basic? The theory proposes that they are made of tiny, vibrating strings of energy. These strings would be unimaginably small. They would be far smaller than atoms, and far smaller than anything we could ever hope to see directly. The core concept is that they vibrate in different patterns, much like the strings of a violin or guitar, and each pattern of vibration would correspond to a different particle. It is a beautiful thought. The entire universe, from the smallest quantum particle to the largest galaxy, could be nothing more than a vast symphony of vibrating strings. Each string is playing its own note in the cosmic composition. If that is true, then the theory of everything isn't just a mathematical framework. It is literally music made manifest. But before we get too carried away by the poetry of it all, we should remember that string theory is still very much a work in progress. It is incredibly mathematically complex. It makes predictions that are almost impossible to test with current technology. And there are aspects of it that even its strongest supporters find puzzling. Still, the fact that such a theory exists at all is remarkable. Mathematicians and physicists have managed to construct a framework that might explain everything from quantum mechanics to gravity in terms of vibrating strings. This is quietly extraordinary. It suggests that reality might be far more elegant and interconnected than our everyday experience suggests. Imagine if the smallest things in the universe were not actually things at all, but songs. To truly appreciate this idea, we must look at how we got here. For most of the 20th century, physicists thought they understood the basic building blocks of reality pretty well. We knew matter was made of atoms. We knew atoms were made of protons, neutrons, and electrons. Then, we discovered that protons and neutrons were themselves made of even smaller particles called quarks. We also found particles that carried forces. We found photons for light and electromagnetic fields. We found gluons for the strong nuclear force. We found W and Z bosons for the weak nuclear force. It was like taking apart a watch and finding springs and gears and tiny wheels, each with its own specific job. We built what is called the Standard Model, a kind of periodic table for all the fundamental particles and forces. It worked beautifully, explaining almost everything we observed in particle accelerators and cosmic ray detectors. But there was always something slightly unsatisfying about this picture. Why these particular particles? Why do they have these specific masses and charges? Why do electrons have exactly the charge they do and not some other value? The Standard Model could describe these properties with incredible precision, but it could not explain why they existed in the first place. And then, sometime in the late 1960s, a few physicists began playing with a radical idea. What if these fundamental particles were not actually fundamental? What if they were all different manifestations of something even more basic? The idea they came up with sounds almost musical. Instead of thinking of electrons and quarks as tiny solid points, what if they were actually tiny loops of vibrating energy? These loops would be unimaginably small, perhaps 10 to the power of minus 35 meters across. That is so small that if an atom was scaled up to the size of our solar system, a string would still be smaller than a tree. But size isn't what makes strings special. What makes them remarkable is that they can vibrate in different ways, like the strings on a guitar or violin. And here is the truly elegant part. Each different vibration pattern corresponds to a different particle. Picture a guitar string for a moment. Pluck it one way, and you get a low, deep note. Pluck it differently, and you get a high, bright tone. The string is the same string, but the different vibration patterns create completely different sounds. In string theory, something similar happens. The same fundamental string vibrating in different patterns appears to us as completely different particles. A string vibrating in one particular way might manifest as an electron with its specific mass and electric charge. The same string vibrating in a different pattern might appear as a photon, massless and carrying light. Another vibration could produce a quark with its own unique properties. It is as if the entire particle zoo, all the electrons and photons and quarks and neutrinos, were really just different notes being played by the same cosmic instrument. This idea is breathtaking in its simplicity and scope. Instead of dozens of fundamental particles, each requiring its own explanation, we would have just one fundamental entity, the string. All the complexity and diversity of the particle world would emerge from the simple fact that strings can vibrate in many different ways. However, the strings in string theory are not quite like the guitar strings we are familiar with. For one thing, they do not need to be attached to anything. A guitar string needs tuning pegs and a bridge to hold tension, but these cosmic strings are fundamental entities. They can exist as tiny, closed loops, circles of vibrating energy floating freely in the vacuum of space. They can also exist as open strings, appearing as snippets with two loose ends that can wiggle and dance through the universe. Furthermore, unlike guitar strings, which vibrate in the familiar three dimensions of everyday space, up and down, left and right, back and forth, these fundamental strings vibrate in additional dimensions that we cannot directly perceive. The mathematics describing how these strings vibrate is extraordinarily complex. It involves concepts drawn from the most advanced frontiers of topology and geometry. Yet, despite the heavy mathematics, the underlying idea remains elegantly simple. At its core, the theory suggests that everything is music. Every particle you can touch, every force you feel, and every field that permeates space is really just a different song being sung by vibrating strings. There is something deeply satisfying about this picture. Throughout human history, music has always seemed to touch something fundamental about reality. We have spoken of the music of the spheres, the rhythm of the seasons, and the harmony of natural processes. String theory suggests that this language might be more than just a poetic metaphor. It might be literally true that the universe is a symphony, with every atom and every star contributing its own voice to the cosmic composition. Of course, we cannot actually hear this music with our ears. The strings are far too small, and their vibrations occur at frequencies far too rapid for biological senses to detect. But in a very real sense, we are the music. Every atom in your body, every thought sparking in your mind, and every beat of your heart is built from this vast, invisible symphony. The idea that particles are really vibrating strings also helps physicists explain one of the biggest mysteries in science: why the mathematical constants of nature have the specific values they do. Consider a musical instrument again. The pitch of a guitar string depends on very specific physical properties: its length, its tension, and its thickness. Change the tension, and the note changes. In string theory, the properties of fundamental particles such as the mass of an electron, the strength of the electromagnetic force, or the speed of light itself are not random numbers. They would depend on the precise way their corresponding strings vibrate. All of these fundamental numbers might be determined by the underlying geometry and dynamics of string vibrations. This offers a picture of reality that is both more complex and more unified than anything we have imagined before. It is complex because it requires additional dimensions and mathematical structures far beyond our everyday experience. Yet, it is unified because it reduces all the apparent diversity of the physical world, all the different particles and forces, to variations on a single theme: the music of vibrating strings. Whether this musical vision of reality is actually correct remains one of the great open questions in physics. We have not yet proven it experimentally, but the very fact that such a theory is mathematically possible, that the laws of mathematics allow for a universe where everything is made of resonance, is itself a kind of wonder. Right now, as you listen to this, you might be surrounded by dimensions you cannot see, touch, or even imagine. This brings us to the most mind-bending aspect of the theory. We live in a world of 3 spatial dimensions. You can move forward and backward. You can move left and right. You can move up and down. That is it. Those are your only options for getting around in space. If you add time as a 4th dimension, you have what physicists call space-time, the 4-dimensional arena in which all of physics takes place. But string theory suggests that this familiar picture is surprisingly incomplete. According to the mathematics required to make vibrating strings work, reality might actually have many more dimensions than the 4 we experience. The equations do not work with just 3 dimensions of space. They require more room for the strings to vibrate correctly. String theory predicts that there are not just 1 or 2 extra dimensions, but perhaps 6 additional dimensions of space. This would make a total of 9 spatial dimensions, plus time, for a 10-dimensional universe. Now, this immediately raises an obvious and difficult question. If there are extra dimensions all around us, right here in this room, why can't we see them? Why can't we move through them? It is not as if we can step sideways into a 5th dimension the way we can step sideways across a kitchen. The answer, according to string theory, is that these extra dimensions are compactified. This is a technical way of saying they are rolled up, folded, and curled so tightly that they are effectively invisible to us. To understand how a dimension can be hidden in plain sight, imagine looking at a garden hose lying across a lawn from a great distance. From far away, the hose looks like a simple one-dimensional line. You can see its length stretching from one end of the yard to the other. You can define a position on that line. But from that distance, you cannot see that the hose actually has width and depth. You cannot see the curve of the tube. The hose is really 3-dimensional. But 2 of those dimensions, the circumference around the tube, are curled up into such a small circle relative to the length that they become invisible from a distance. In string theory, something similar might be happening with the fabric of space itself. What we perceive as a 0-dimensional point in our familiar 3-dimensional space might actually be a tiny, complex shape in 9 dimensions. The extra dimensions are there, everywhere we look, but they are curled up so small, far smaller than atoms, far smaller than the nucleus of an atom, that we have no physical way of directly experiencing them. Think of it this way. If you are a tiny ant walking along that garden hose, you can move in two very different ways. You can walk along the long length of the hose, traveling large distances that anyone watching from far away can easily see. This represents our familiar 3 dimensions. But as an ant, you can also walk around the circumference of the hose. You can follow a tiny circle that brings you right back to where you started without ever moving forward along the hose. From the ant's perspective, both directions, the long length and the short circle, are equally real. But from our distant perspective, as human observers, only the motion along the length of the hose is visible. We are blind to the circular motion. In this analogy, we are like the distant observers. We are enormous creatures compared to the scale of strings. We can see and move through the 3 large dimensions of space, the length of the universe, but we are completely unaware of the tiny circular journeys that might be possible in the compactified dimensions. We simply cannot fit inside them. But these hidden dimensions are not just mathematical curiosities or places to hide. In string theory, they play a crucial role in determining the properties of the particles we observe. The way the extra dimensions are curled up, their specific shape, size, and topology affects how strings can vibrate within them. And since different vibrations correspond to different particles, the geometry of the extra dimensions would directly influence the physics we observe in our 3-dimensional world. It is a bit like the way the shape of a musical instrument affects the sounds it can make. Imagine a violin and a guitar. They might have strings of similar length and tension. However, if you pluck them, they produce very different sounds. This is because of the different shapes of their bodies, the wood, the curves, the internal cavities. All of these physical shapes contribute to the resonance of the final music. In string theory, the hidden dimensions play a similar role to the body of the instrument. They are like the body of a cosmic instrument, shaping and coloring the vibrations of the strings. The way these dimensions twist and fold determines which particles can exist and what properties, like mass and charge, those particles will have. This leads to one of the most remarkable and dizzying predictions of string theory. There might be many different ways to curl up these extra dimensions. In fact, there might be billions upon billions of ways to fold them, and each different configuration would correspond to a different possible universe with different laws of physics. Our universe, with its particular electron mass, its specific gravity, and its precise speed of light, would be just one of many possibilities. It would be the result of one particular way of folding up the hidden dimensions. In another universe, the dimensions might be folded differently, resulting in particles and forces that are completely alien to us. The mathematical shapes that describe these folded dimensions are often fantastically complex. They have names like Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xingtung Yau, who first studied them. These shapes exist in 6 dimensions, which is already hard enough for the human mind to visualize. But they have intricate internal structures with holes, tunnels, and connections that would make a 3-dimensional maze look simple by comparison. And yet, despite their complexity, these hidden shapes might be everywhere. This is the part that truly shifts our perspective. Every point in empty space, every location where you could place your finger right now, might not be just a point. It might be a tiny, incredibly detailed 6-dimensional sculpture. The space around you, the space between your eyes and this screen, would not be empty. It would be filled with structure so fine and folded that it escapes all notice. There is something both humbling and wonderful about this idea. It suggests that reality is far richer and more complex than our senses can detect. We move through the world thinking we understand space. We think that what we see is what there is. But we might be like creatures living on the surface of a vast ocean, completely unaware of the depths and currents moving below us. These hidden dimensions also offer a possible solution to some long-standing puzzles in physics, such as the weakness of gravity. Why is gravity so much weaker than the other forces? Think about a small magnet picking up a paperclip. That tiny magnet is overcoming the gravitational pull of the entire Earth. Gravity is incredibly weak compared to electromagnetism. In string theory, this might be because gravity is not confined to our three dimensions. Gravity might be diluted by spreading out into the extra dimensions, leaking away from our world, while the other forces are confined to our three-dimensional brain, our slice of the higher dimensional space. Of course, we must remember that the existence of extra dimensions remains purely theoretical. We have no direct evidence for them. We have no way of seeing or measuring them with current technology. They exist in the mathematics of string theory, but whether they exist in physical reality is still an open question. But the possibility alone is enough to change how we think about space and existence. It reminds us that the universe might be stranger and more wonderful than our everyday experience suggests. Right now, as you rest and let your mind wander, you might be floating not just through the familiar dimensions of space and time, but through hidden dimensions folded so tightly they fit in the space between your thoughts. This brings us to a profound question. What if gravity, electricity, and the forces that hold atoms together were all just different instruments in the same cosmic orchestra? In our everyday world, we experience these forces as completely different things. Gravity keeps your feet on the ground and makes apples fall from trees. It is always attractive, always pulling things together. It seems to work across infinite distances, though it gets weaker as things move apart. Then there is the electromagnetic force. It gives us lightning and magnetism, runs our electrical devices, and holds atoms together through chemical bonds. Unlike gravity, electromagnetic forces can both attract and repel. They are also much stronger than gravity, but they can be shielded and blocked. Then there are two forces we do not experience directly, but that are crucial for the existence of matter. The strong nuclear force holds the centers of atoms together, binding protons and neutrons despite their tendency to push apart. The weak nuclear force is responsible for radioactive decay and plays a key role in the nuclear reactions that power the sun. For much of the 20th century, physicists treated these four fundamental forces as completely separate phenomena. Each required its own mathematical description and its own set of rules. It was like having four different orchestras playing in different concert halls, each with its own conductor and style. But gradually, physicists began to notice connections. In the 1960s and 70s, they discovered that the electromagnetic force and the weak nuclear force were actually two aspects of a single, unified electro-weak force. At high energies, or at very high temperatures like those just after the Big Bang, these two forces become indistinguishable. They merge into one. This was like realizing that two different orchestras were actually sections of the same larger ensemble. Encouraged by this, scientists tried to unify the electroweak force with the strong nuclear force, creating grand unified theories. These theories suggested that at even higher energies, all three forces would merge. However, the picture remained incomplete because gravity was always the odd one out. Gravity is much weaker than the other forces. It affects everything with mass or energy. And unlike the others, Einstein showed us that gravity is not really a force at all, but the curvature of space-time itself. This makes it very difficult to fit into the same mathematical framework as the other forces. This is where string theory offers something genuinely revolutionary. In string theory, all four fundamental forces arise from the same basic phenomenon: vibrating strings. Different vibration patterns of the same fundamental strings would give rise to the particles that carry each of the different forces. The particle that carries electromagnetic force, the photon, would correspond to strings vibrating in one particular way. The particles that carry the strong nuclear force, called gluons, would be strings vibrating in a different pattern. The W and Z bosons that carry the weak nuclear force would represent yet other vibration modes. And gravity? In string theory, gravity would be carried by a particle called the graviton. This would correspond to strings vibrating in a very specific way as closed loops rather than open strings. This difference in shape might explain why gravity seems so different from the others. It is not that gravity is fundamentally alien. It is just that its string has a different topology. This would mean that the four fundamental forces are not four different things. They would be four different melodies played by the same cosmic instrument. The universe would be like a single, incredibly complex symphony, where different sections play different themes that combine to create physical reality. String theory goes even further. It suggests that the distinction between matter and forces might also be an illusion. The vibrations that create stuff, like electrons, and the vibrations that create forces like gravity are just different aspects of the same underlying string dynamics. Everything emerges from the same basic phenomenon: strings vibrating in the fabric of space-time. This leads to one of the most beautiful aspects of string theory: its mathematical consistency. Unlike other attempts to unify physics, string theory doesn't force mismatched puzzle pieces together. The unification emerges naturally. The theory predicts that at extremely high energies, like the first moments after the Big Bang, all forces would indeed merge into one. As the universe cooled, this single unified force would have broken apart, like light splitting into different colors through a prism, giving rise to the four distinct forces we observe today. There is something deeply satisfying about this picture. It suggests that beneath the complexity of the world, there is a profound simplicity. The electricity in your nerves, the gravity holding the Earth in orbit, and the nuclear fire of the stars would all be variations on the same theme. Of course, proving this remains a great challenge. We cannot recreate the energies of the Big Bang in a lab. We can only look for indirect evidence. But the possibility alone changes how we think about the world. Every time you flip a switch or feel the ground beneath you, you might be experiencing the music of vibrating strings, resonating through hidden dimensions. At the smallest scales imaginable, however, reality starts to behave like a jazz improvisation, where the notes change every time you listen. This is the world of quantum mechanics. Quantum mechanics has always been the strange cousin in the family of physics. Unlike the predictable clockwork of classical physics, the quantum world is uncertain. Particles do not have definite positions until you measure them. They can exist in multiple states simultaneously, or tunnel through barriers that should be impossible to cross. This uncertainty is built into the very fabric of reality. It is as if the universe is constantly making choices about what to be. For decades, physicists struggled to fit this quantum weirdness together with gravity. In standard quantum mechanics, point particles can pop into existence out of nothing, borrowing energy from the vacuum. This creates a chaotic quantum foam at small scales. String theory offers a new perspective on these mysteries. Instead of thinking about point particles, string theory asks us to imagine tiny loops and segments of energy vibrating through space and time. This simple change leads to remarkable consequences. One of the most striking things about strings is that they are extended objects, not mathematical points. A string has length. This means strings have a natural minimum size. They can only get so close to each other before their stringy nature matters. This helps resolve the mathematical infinities that plague other theories. When physicists calculate interactions between point particles, they often get infinite, meaningless answers because points can get infinitely close to each other. But string interactions are finite. Think of it like the difference between balancing two sharp needles point to point versus balancing two guitar strings. The needles can theoretically touch at a single, infinitely small point, creating an unstable situation. The guitar strings, being extended objects, interact over their entire length. This creates a stable, well-defined interaction. String theory also offers a new way to understand quantum uncertainty. In traditional physics, uncertainty is just a rule we have to accept. In string theory, this uncertainty might reflect the fact that strings are constantly vibrating. Imagine trying to photograph a vibrating guitar string. Even with a fast camera, you would never capture it perfectly at rest. It would always be blurred. Similarly, the properties of fundamental particles might be blurred because the underlying strings are never at rest, always vibrating between different configurations. But string theory's approach to quantum mechanics goes deeper than just providing a new metaphor for uncertainty. The mathematics of string theory naturally incorporates quantum principles in a way that seems more elegant and self-consistent than previous approaches. For instance, the theory requires the existence of something called supersymmetry. This is a deep, conceptual symmetry that connects particles of different types. In a supersymmetric universe, every known particle has a heavy, invisible partner particle with slightly different properties. Think of it like a cosmic balancing act. For every electron, there is a selectron. For every quark, a squark. While we have not yet found these partner particles in our colliders, mathematically, they serve a crucial purpose. These partnerships help stabilize the quantum fluctuations that otherwise tend to run wild in theories of quantum gravity. They calm the mathematics down. The theory also suggests a radical rethinking of the quantum foam, the bubbling, chaotic uncertainty that exists at the smallest scales of space and time. In standard quantum mechanics, this foam is described as virtual particles violently popping in and out of existence from nothingness. It is a jagged, abrupt process. String theory softens this picture. It suggests that this bubbling activity might actually be composed of tiny strings splitting and joining. Instead of particles blinking on and off like broken light bulbs, we would have strings dividing like biological cells in mitosis, or joining together like a cosmic marriage. The quantum dance becomes a string dance. It becomes a flowing, continuous choreography, rather than a series of abrupt appearances and disappearances. One of the most beautiful aspects of how string theory handles quantum mechanics is its approach to the measurement problem. This is the famous puzzle of how and when hazy quantum possibilities collapse into definite realities. In string theory, this collapse might be understood as strings settling into particular vibration patterns after interacting with their environment. It is as if each string interaction is a musical conversation. Before the interaction, each string might be vibrating in a superposition of different modes, like a complex chord with multiple notes playing simultaneously. The interaction between strings would be like a musical dialogue where the different possible notes influence each other, adjusting and modulating until they settle into a harmonious resolution. This picture suggests that quantum uncertainty is not just a mysterious, annoying feature of nature that we have to accept. Instead, it is a natural consequence of the underlying musical structure of reality. The universe improvises because it is literally made of music, and music, by its very nature, flows and changes. It creates new harmonies through the interaction of different voices. Of course, we must be clear that all of this remains highly theoretical. We do not yet have experimental evidence for the existence of strings. The mathematical machinery required to make precise predictions from string theory is extraordinarily complex, but the framework offers a compelling new way to think about the quantum nature of reality. As you settle deeper into relaxation, your brain activity slowing, your thoughts becoming softer and less defined, you might imagine that you are participating in this quantum dance yourself. Every atom in your body, every chemical reaction in your cells, and every electrical impulse firing in your neurons would be part of this vast improvisation. It is a cosmic jazz session where tiny strings vibrate their way through the hidden dimensions of space and time, creating the music that is you. However, amidst all this harmony, there has always been one discordant note: gravity. Gravity has always been the odd one out in physics. It is like the friend who shows up to parties but never quite fits in with the group. While the other three fundamental forces, electromagnetic, strong nuclear, and weak nuclear, all play by quantum mechanical rules, gravity seems to march to the beat of its own drummer. Albert Einstein showed us that gravity is not really a force in the traditional sense. It is the curvature of space-time itself. Massive objects, like stars and planets, warp the fabric of space and time around them. Much like a bowling ball resting on a soft mattress curves the surface, what we experience as gravitational attraction is really just objects sliding along the curves in this warped space-time. It is a beautiful and elegant picture. It works wonderfully for describing everything from falling apples to orbiting planets, and even the expansion of the entire universe. But when physicists try to apply quantum mechanics to gravity, everything breaks down. The problem becomes apparent when you try to describe what happens at the smallest scales, where both gravity and quantum effects should be important. Consider the interior of a black hole, where matter is compressed to near infinite density according to Einstein's equations. Or think about the very first moment of the Big Bang, when all the matter and energy in the observable universe was packed into a volume smaller than a proton. In these extreme conditions, you cannot ignore quantum mechanics. The uncertainty principle tells us that at very small scales, space and time themselves should start to fluctuate wildly. Virtual particles should be popping in and out of existence, borrowing energy from the vacuum and paying it back in tiny slivers of time. But here is the catch. These quantum fluctuations carry energy, and since energy creates gravity, these fluctuations would create intense, microscopic gravitational fields. These fields would then influence the quantum fluctuations, which would create more gravity, creating a runaway feedback loop. The mathematics explodes into meaningless infinities. It is like trying to tune a guitar while someone is violently shaking the tuning pegs. Every adjustment you make gets amplified and distorted by the shaking, making it impossible to find a stable, harmonious state. For decades, physicists tried various approaches to solve this problem. They attempted to apply the same mathematical techniques that had successfully merged quantum mechanics with electromagnetism. but gravity proved stubbornly resistant. Part of the difficulty is that gravity is so much weaker than the other forces, but it is also universal. Everything with mass or energy creates and responds to gravitational fields. You cannot turn it off. String theory offers what might be the first truly successful approach to quantum gravity. The key insight is that gravity in string theory is not treated as something fundamentally different from the other forces. Instead, it emerges naturally from the vibrations of closed strings. In string theory, the particle that would carry the gravitational force is called the graviton. Unlike the particles that carry the other forces, like the photon or the gluon, which correspond to open strings with two free ends, the graviton corresponds to a closed string. It is a loop with no ends at all. This difference in topology, this difference in shape, might be exactly why gravity behaves so differently from the other forces. Closed strings can vibrate in ways that open strings cannot. They can twist, they can change size, expanding and contracting like a rubber band. They can oscillate in complex patterns that span all the dimensions of space, including the hidden ones. When a closed string vibrates in its lowest energy mode, its simplest pattern, the result looks exactly like what we would expect from a graviton, a massless particle that couples to energy and momentum in precisely the way that Einstein's theory predicts. But string theory goes further than just providing a quantum description of individual gravitons. It offers a complete framework for understanding how space-time itself emerges from string dynamics. In this picture, the smooth, continuous space-time of Einstein's relativity would be an approximation. It is valid at large scales, like when we look at planets or stars, but it breaks down when you zoom in far enough to see the underlying string structure. Imagine looking at a high-resolution photograph from far away. From a distance, it appears to be a smooth, continuous image with perfect blending of colors. But if you walk up to it and look closely enough with a magnifying glass, you can see that it is actually made up of discrete pixels, tiny dots of different colors that combine to create the illusion of smoothness. String theory suggests that space-time might be similar. It appears smooth and continuous at the scales we normally experience, but it is actually composed of something more fundamental when examined at the smallest possible scales. This pixelated view of space-time helps resolve many of the problems that plague other approaches to quantum gravity. The infinities that arise when point particles interact in curved space-time are naturally cut off at the string scale. Instead of trying to make sense of physics at arbitrarily small distances that mathematically shrink to zero, string theory suggests that there is a minimum meaningful size. There is a resolution limit below which the very concept of distance breaks down. You cannot zoom in further than the string itself. String theory also provides a natural explanation for why gravity is so much weaker than the other forces. In the framework of extra dimensions, gravity might be the only force that can spread out into all the dimensions of space. Think of it like sound. If you shout in an open field, the sound waves spread out in all directions, up, down, left, right. The energy is diluted, so the sound gets quieter quickly as you move away. But if you shout into a tube, the sound is confined. It travels much further without losing strength. In string theory, electromagnetic and nuclear forces might be confined to our familiar three-dimensional world, like sound in a tube. But gravity corresponds to closed strings. As we will see, closed strings are free to leave the tube. They can wander off into the extra, hidden dimensions. This dilution effect would make gravity appear much weaker to us than it actually is. simply because a large portion of its strength is leaking into places we cannot see. Perhaps most remarkably, string theory suggests that the relationship between gravity and quantum mechanics is not one of conflict, but of deep complementarity. The quantum uncertainties that seem to destroy the smooth space-time of relativity might actually be the very thing that creates space-time in the first place. It is a picture where reality emerges from music, where the vibrations of fundamental strings create not just particles and forces, but space and time themselves. Gravity would not be the odd one out anymore. It would be part of the same cosmic symphony, played by closed strings vibrating through the hidden dimensions of a universe far stranger and more musical than we ever imagined. The mathematics is still being worked out, and experimental confirmation remains elusive. But for the first time, physicists have a framework that might actually solve the gravity problem, not by forcing quantum mechanics and relativity to coexist, but by showing that they are both aspects of something even more fundamental: the music of vibrating strings resonating through the fabric of reality itself. To understand this deeper, we must look at the shapes of the strings themselves. Some strings have ends that wiggle freely, while others form perfect loops like cosmic rubber bands with no beginning or end. In the world of string theory, topology, the mathematical study of shapes and connections, becomes as important as the more familiar concepts of mass and energy. The difference between a string with two free ends and a string that closes in on itself to form a perfect loop might seem like a minor detail, but it leads to profound consequences for the kinds of particles and forces that emerge from string vibrations. Let's look at open strings first. Open strings are perhaps easier to visualize. Picture a tiny segment of thread, so small it would make an atom look like a planet floating freely in space. Both ends of this thread can vibrate independently, wiggling back and forth like the ends of a jump rope held by two invisible hands. These vibrations propagate along the length of the string, creating standing wave patterns that determine what kind of particle the string appears to be to our instruments. But here's the crucial question. If an open string has loose ends, where are those ends located? The key feature of open strings is that their endpoints are free to move, but they cannot just move anywhere. In most versions of string theory, the endpoints of open strings are confined to what physicists call D-branes. The term D-brane sounds technical, but you can think of them as cosmic membranes. Imagine vast, thin sheets stretched through space. These sheets might extend through our three familiar dimensions, or they might extend through some of the extra dimensions that string theory requires. Our familiar three-dimensional world, the universe we see, the room you are sitting in, might actually be one of these D-branes. It could be a three-dimensional surface embedded in a higher dimensional space, much like a single sheet of paper floating in the middle of a room. The endpoints of open strings would be stuck to our brain like flies stuck to flypaper. They can slide around on the surface, they can meet other strings and interact, but they cannot leave the surface. They are tethered. This confinement might explain why we observe particles moving through three-dimensional space, but not through the additional dimensions that string theory predicts. The photons that make up light, the electrons that make up our atoms, these are all open strings. Their ends are pinned to our 3D brain. They simply cannot escape into the higher dimensions. They are trapped on this slice of reality. The vibrations of these open strings, tethered to our slice of reality, give rise to many of the particles we know and love. Electrons, quarks, photons, all the building blocks of atoms and light could be nothing more than different vibrational modes of open strings. Each different pattern of vibration, each different standing wave rippling along the string's length, would correspond to a particle with different properties. One note creates mass, another creates electric charge, yet another determines how the particle spins. But because open strings have endpoints that are confined to D-branes, they have limitations. They are shackled. Consequently, the forces they create are also confined. The electromagnetic force that lights our cities, the nuclear forces that bind the heart of the atom, all interactions between matter particles would be restricted to the same three-dimensional brain that we inhabit. They are trapped here with us. They cannot spread out into the additional dimensions of space. This is where the magic of the closed string appears. Closed strings are fundamentally different because they have no endpoints to confine them. They are perfect loops. Without loose ends to get stuck on the D-brane flypaper, closed strings are free. They are free to move through all the dimensions of space, including the hidden ones that we cannot directly perceive. They are like cosmic hula hoops, free to rotate, float, and vibrate in ways that open strings simply cannot. And this freedom is the key to understanding gravity. The lowest energy vibration mode of a closed string produces what string theorists call a graviton. This is the hypothetical particle that carries the gravitational force. Unlike the particles produced by open strings, gravitons are travelers. They are free to propagate through all the dimensions of space. They can leave our three-dimensional world and drift into the higher dimensional bulk. This freedom might explain the long-standing mystery of why gravity is so much weaker than the other forces. If gravity is carried by closed strings, it is not confined to our three-dimensional brain. Instead, it spreads out through the additional dimensions, becoming diluted in the process. To understand this, imagine shouting in a narrow, concrete hallway. The walls confine the sound waves. All the sound energy is concentrated in a small space, directed forward. Your voice sounds loud, booming, and clear. This is like the electromagnetic force, strong and concentrated because it is trapped in fewer dimensions. Now, imagine standing in the middle of a vast, open cathedral with a high vaulted ceiling, or perhaps standing on a mountain peak. You shout with the same force, using the same amount of energy, but here, the sound spreads out in all directions, up, down, and sideways. It fills the vast volume of air. To a listener standing nearby, your voice seems much fainter, much softer. Gravity might be like the voice in the cathedral. It permeates the dimensions we can't perceive, spreading its energy across a vast, invisible volume. What we experience as gravity here on Earth, the pull that keeps us grounded, might be just a tiny fraction of its true strength. It is merely the echo that remains after the rest of the force has leaked away into the hidden dimensions. Closed strings can also vibrate in more complex ways than open strings. Because they are loops, they can twist, they can change their size, expanding and contracting. They can oscillate in patterns that have no equivalent in open string vibrations. Some of these vibration modes might correspond to particles and fields that we haven't discovered yet. They could form exotic types of matter and energy that interact so weakly with ordinary matter, our open string matter, that they have completely escaped detection by our instruments. The distinction between open and closed strings also has profound implications for the structure of space-time itself. Open strings, confined to D-branes, interact primarily with the geometry of those branes. They feel the shape of the surface they live on, but closed strings interact with the geometry of all space, including the hidden dimensions. This suggests a dynamic relationship. The vibrations of closed strings might actually determine the shape and size of the extra dimensions. They might be dynamically adjusting the geometry of space in response to the matter and energy present This leads to one of the most intriguing and radical possibilities in string theory. The idea that the familiar three-dimensional space we inhabit might not be fundamental at all. It might be emergent. Think of the surface of a calm lake. To an insect walking on it, the surface looks like a distinct two-dimensional sheet. It supports weight. It has properties. But we know that the surface is not a separate object. It is merely the interface between the air above and the water below. It emerges from the interactions of the fluid molecules. Similarly, our three-dimensional world, our brain, might emerge from the complex interactions of strings in higher dimensional space. We might be living on the surface of a much deeper reality. Some versions of string theory even suggest that open and closed strings can transform into one another under certain conditions. Imagine an open string wiggling on our brain. If its two loose ends drift close enough and touch, they could fuse together. The string becomes a closed loop. Instantly, it is no longer tethered to our world. It could detach and float away into the hidden dimensions. This would look, to us, like a particle disappearing from our universe, vanishing into thin air. Conversely, a closed string floating in the bulk space could drift close to our brain and break apart, its two ends snapping onto the surface. To us, this would look like a new particle appearing seemingly from nothing. The mathematics describing these processes is extremely complex. It involves concepts from advanced geometry and topology that push the boundaries of current mathematical knowledge. But the basic picture it paints is elegantly simple. Reality emerges from the interplay between two kinds of cosmic music: the confined melodies of open strings playing on the surface of three-dimensional brains, and the free-flowing harmonies of closed strings resonating through all the dimensions of space. Whether this picture corresponds to physical reality remains an open question. We have no direct evidence yet for the existence of D-brains, extra dimensions, or the strings themselves. But the mathematical consistency and elegance of the framework continue to attract the brightest minds in physics. It offers hope that the fundamental nature of reality might be far more musical and interconnected than our everyday experience suggests. As you drift towards sleep, your consciousness settling like ripples on that quiet pond, you might imagine yourself as part of this cosmic string ensemble. Your thoughts and dreams are emerging from the gentle vibrations of open strings confined to our three-dimensional brain, while gravity and space-time itself flow from the deeper harmonies of closed strings, dancing through dimensions beyond perception. But this journey leads us to an even larger question. What if our universe is just one bubble in an endless bath, floating alongside countless others we will never see? String theory doesn't just suggest that our universe might be made of vibrating strings. It implies something far more extraordinary, that our universe might be just one of an infinite number of possible universes, each with its own laws of physics, its own particles, and its own story. This idea emerges naturally from the mathematics of string theory, even though it is one of the most difficult concepts to wrap our minds around. Remember that in string theory, the properties of particles and forces mass, charge, gravity depend on how the extra dimensions are curled up and folded. But here is the catch. There isn't just one way to fold up 6 extra dimensions into tiny hidden shapes. There are many ways. In fact, the mathematics suggests there are perhaps 10 to the power of 500 ways to fold these dimensions. That is a 1 followed by 500 zeros, a number far larger than the total number of atoms in the observable universe. Each different way of folding the extra dimensions like a different piece of cosmic origami would create a universe with different physics. In one universe, electrons might be heavier or perhaps lighter than air. In another, the force of gravity might be stronger, crushing stars before they can shine, or weaker, allowing matter to drift apart forever. In yet another, there might be entirely different particles that don't exist in our reality, creating forms of matter we cannot comprehend. The mathematical landscape of these possibilities is so vast that physicists call it simply the landscape. It is a terrain of potential realities stretching beyond the horizon of imagination. Think of it like a vast, infinite garden. In this garden, every flower represents a different possible universe. Some flowers might be very similar to each other, like neighboring universes, where the only difference is the mass of a single, obscure particle. Others might be wildly different, with completely different organizing principles, different numbers of forces, or different ways of structuring matter and energy. Our universe would be just one flower in this infinite garden. It is special to us because it is the only one we can see, the only one we can inhabit. But it is not necessarily unique or privileged in any objective sense. This brings us to a concept known as the anthropic principle. It suggests that we exist in this particular universe not because it is the correct one mathematically, but simply because it is the one that allows for the existence of stars, planets, chemistry, and life. In universes where the forces are too strong or too weak, where particles cannot form stable atoms, or where space-time itself is unstable, there would be no observers. There would be no one to look up at the sky and wonder about the nature of reality. Those universes exist in the landscape, but they remain silent and empty. This selection effect is similar to looking at a photograph of a large crowd where everyone is smiling. You might conclude that all humans must be happy all the time, but really, you are just looking at a wedding photo, a specific situation where people were arranged to smile. We observe the physical constants and laws that we do, not because they are the only possible values, but because they are among the rare few values that allow for observers like us to exist. But the multiverse of string theory goes beyond just different values for familiar physical constants. In some regions of this landscape, the very structure of reality might be different. There might be universes where space has different numbers of dimensions, perhaps 2 or 5 or 10. There might be places where time flows differently, or where the basic categories of matter and energy do not apply. Some physicists find this proliferation of possibilities troubling. If string theory predicts that almost anything is possible somewhere in the multiverse, then does it really predict anything specific about our universe? It risks becoming less like a scientific theory that explains why things are the way they are, and more like a framework that accommodates any possible observation. Others, however, find the multiverse idea liberating. It suggests that the apparent fine-tuning of our universe, the fact that gravity is just right, that the electron charge is just right, isn't evidence for some cosmic design or impossible luck. Instead, it is a natural consequence of selection effects in an infinite landscape of possibilities. We exist in a universe suitable for life because universes unsuitable for life don't produce observers to comment on their unsuitability. The multiverse also offers a potential explanation for some of the puzzling features of quantum mechanics we discussed earlier. In our discussion of quantum uncertainty, we saw how particles seem to exist in multiple states simultaneously until observed. In a multiverse interpretation, these multiple states might correspond to the particle actually existing in different states in different universe branches. What we interpret as quantum uncertainty might simply be our limited perspective on a reality that includes all possible outcomes. But perhaps the most profound implication of the multiverse is what it suggests about the nature of existence itself. If every mathematically consistent possibility is realized somewhere in the landscape, then reality becomes not a single story, but an infinite library containing every possible story, every decision not made, every path not taken. Every alternative history would exist somewhere in the vast space of possibilities. This doesn't mean that we could ever visit or communicate with other branches of the multiverse. The different universe bubbles would be causally disconnected from each other, separated by regions of space and time that expand faster than light can travel between them. Each universe would be an island of reality in an infinite sea of possibilities. There is something both humbling and comforting about this picture. Humbling because it suggests that our entire observable universe, with its billions of galaxies and trillions of stars, might be just one tiny bubble in an inconceivably vast foam of realities. Yet, it is also comforting. It suggests that every possibility, every potential for beauty, complexity, and meaning is realized somewhere in the full scope of existence. We must be clear. String theory does not definitively predict that the multiverse exists in the way a weather forecast predicts rain. Rather, the mathematics allows for it, proving that other universes actually exist, rather than just being mathematical possibilities on a chalkboard, remains one of the deepest challenges in theoretical physics. By definition, we can only observe our own universe. We are trapped in our own bubble. So, evidence for other universes must be indirect. We might look for subtle signatures in the cosmic microwave background radiation, faint scars from when our bubble might have bumped into another bubble eons ago. But the very fact that our most sophisticated theories naturally lead us to contemplate infinite gardens of reality suggests that the cosmos might be far stranger and more abundant than our ancestors ever dreamed. As you settle deeper into relaxation and let your consciousness explore the landscape of dreams, you might imagine yourself floating through this vast garden of possibilities. Each dream is a glimpse of what reality might be like in some distant branch of the infinite tree of existence. But to truly understand how these different universes could exist, we need to return to the source of their differences, the hidden dimensions. Specifically, the idea that 6 extra dimensions might be curled up inside every point in space, smaller than the smallest thing you can imagine. We have touched on the idea of extra dimensions before, but it is worth taking a gentle, closer look at just how strange and wonderful this concept really is. If string theory is correct, then every point in the space around you, every location where you could place your fingertip right now, is not really a simple zero-dimensional dot. Instead, it is a tiny, incredibly complex 6-dimensional shape. It is folded, twisted, and curled in ways that make the most intricate origami look like child's play. These shapes have names that sound like they belong in a fantasy novel. Calabi-Yau manifolds. They are named after the mathematicians Eugenio Calabi and Xingtung Yau, who studied their mathematical properties decades before anyone thought they might be relevant to physics. Despite their exotic names, these geometries might be the most fundamental aspect of reality. They are the hidden architecture, the invisible skeleton that determines why the universe works the way it does. To get a sense of how dimensions can hide inside a point, let's start with a simpler example from our everyday world. Imagine you are looking at a basketball from across a large gymnasium. From that distance, the ball appears to be a perfect sphere, a simple, smooth, 3-dimensional object. You can define its center, its radius, and its surface. But if you could walk up to it and zoom in with incredible magnification, you would see that the surface is not smooth at all. It has texture. It has tiny bumps, pebbles, and valleys that create the grip patterns basketball players rely on. Zoom in even further, and you would see the molecular structure of the rubber, a complex, three-dimensional network of chains and voids that is completely invisible from a distance. In string theory, something similar is happening with space itself. But here, the hidden structure exists in additional dimensions rather than just fine-scale detail in the familiar ones. Every point in our three-dimensional space is like that basketball, apparently simple from our perspective, but actually possessing an intricate internal structure that extends into dimensions we cannot directly perceive. But why 6 extra dimensions specifically? Why not 2 or 10? The answer comes from the rigorous mathematical requirements of string theory. For the theory to be mathematically consistent, to avoid the nonsensical infinities and contradictions that plague other approaches to quantum gravity, the total number of spatial dimensions must be precisely 9. We experience 3 of these dimensions directly: length, width, and height. So, simple subtraction leaves us with 6 dimensions that must somehow be hidden from our everyday experience. These 6 dimensions cannot just be rolled up randomly like a crumpled piece of paper. They must be folded according to very specific mathematical rules to preserve the symmetries that string theory requires. The resulting shapes, the Calabi-Yau manifolds, are the solutions to these complex geometric equations. They are 6-dimensional sculptures that exist in the abstract mathematical realm of topology and differential geometry. Trying to visualize a 6-dimensional shape is essentially impossible for our 3-dimensional brains. We simply don't have the mental software for it. But mathematicians have found ways to represent slices or projections of these structures in forms we can somewhat comprehend. Imagine starting with a sphere. Then, imagine adding handles to it, like the handle on a coffee mug, connecting different parts of the surface. Then, imagine adding more complex structures, holes that tunnel through the shape in various directions, twisting and turning. Now, imagine doing this not in 3 dimensions, but in 6. Imagine connections and tunnels that can twist through dimensions we can't picture. The resulting shape might have hundreds or thousands of holes, tunnels, and connections, all packed into a space so small it makes atoms look enormous. But these are not just abstract mathematical curiosities to be admired. In string theory, the specific shape of the Calabi-Yau manifold at each point in space determines the physics we observe. Remember that strings vibrate, but they don't vibrate in a void. They vibrate through these extra dimensions. The way a string vibrates depends on the geometry it is vibrating through, just as the sound of a wind instrument depends on the shape of the pipe the air is moving through. Different types of holes and connections in the manifold correspond to different particles and forces. A manifold with one specific arrangement of tunnels might force strings to vibrate in a way that creates particles with the mass and charge of an electron. A manifold with a slightly different geometric feature might produce a completely different spectrum of particles. In this sense, the 6-dimensional shape acts like a cosmic instrument, a flute or a violin body, and the strings vibrating through it create the music we observe as physical reality. This leads to one of the most remarkable implications of hidden dimensions: the possibility that different regions of space might have slightly different 6-dimensional geometries. If the shape of the manifold determines the laws of physics, then different shapes mean different laws. What we think of as the immutable, eternal laws of physics, the speed of light, the strength of gravity, might actually be local properties. They might be unique to our particular neighborhood in the higher dimensional landscape. The compactification of extra dimensions also offers potential explanations for some of the deepest mysteries in physics. Why do particles have the masses they do? Why are the forces exactly as strong as they are? Why does space have 3 large dimensions instead of 2 or 4 or 17? All of these questions might have answers that lie in the specific 6-dimensional geometry folded up at every point in space. There is also the tantalizing possibility that these hidden dimensions might not be completely static. Like everything else in the universe, they might be dynamic. They might slowly evolve over cosmic time, gradually changing shape as the universe expands and cools. This evolution could lead to slow drifts in physical constants effects so gradual that they would be difficult to detect over human timescales, but that might leave subtle signatures in the ancient light from distant galaxies. Some versions of string theory even allow for the possibility that the extra dimensions might be larger than we think, large enough to have consequences that could be detectable in our high-energy particle collisions. If particles can access these larger extra dimensions, they might appear to disappear from our 3-dimensional world, carrying energy and momentum into the hidden directions of space. The mathematics of Calabi-Yau manifolds is so complex that even with modern supercomputers, physicists have only been able to study a tiny fraction of the potentially infinite number of possible 6-dimensional geometries. Each one corresponds to a different possible physics, a different way the universe could work. Our particular geometry, the one that produces the electron, the photon, and the gravity we know, is just one point in this vast landscape of mathematical possibilities. As you rest and let your mind wander towards sleep, you might imagine these hidden dimensions folded up inside every atom of your body. Think of them as tiny 6-dimensional gardens, more complex than the most intricate cathedral, all nested within spaces smaller than the smallest things you can conceive. Every breath you take, every thought you think, emerges from strings vibrating through these invisible geometries. You are music played in dimensions beyond perception, but the complexity doesn't stop there. String theory predicts that every particle you know might have a secret twin, a shadow partner dancing just out of sight. One of the most elegant and mysterious predictions of string theory is that every particle in the universe should have a partner, a shadow twin, with properties that mirror and complement its own. This idea is called supersymmetry, and it suggests that the fundamental structure of reality is even more intricate and balanced than we ever imagined. To understand supersymmetry, it helps to think about the 2 basic categories of particles that exist in nature. The particle zoo is divided into 2 distinct tribes. First, there are the particles that make up matter, like electrons and quarks. These are the bricks of the universe. They have a property called half-integer spin, and they are collectively called fermions, named after the physicist Enrico Fermi. Then there are the particles that carry forces, like photons, which carry light, and the theoretical graviton, which carries gravity. These are the mortar that holds the bricks together. They have integer spin, and they are called bosons, named after the physicist Satyendra Nath Bose. Fermions and bosons behave very differently. You could think of them as having different personalities. Fermions are loners. They are the introverts of the particle world. They obey a rule called the Pauli exclusion principle, which essentially means that no 2 identical fermions can occupy the same quantum state at the same time. They need their personal space. This antisocial behavior is actually crucial. It is what gives matter its structure and solidity. Electrons in atoms are forced to stack up in different energy levels because they cannot all crowd into the lowest level. If fermions were not loners, all matter would collapse. Bosons, on the other hand, are gregarious. They are the extroverts. They love to bunch up together in the same quantum state. They can overlap and merge. This is what allows for phenomena like laser light, where billions of photons march in perfect synchronization, all doing exactly the same thing at the same time. Supersymmetry proposes a bridge between these two tribes. It suggests that for every fermion in nature, there is a corresponding boson, and vice versa. Every matter particle would have a force-carrying partner, and every force-carrying particle would have a matter-like twin. The names given to these partners follow a whimsical convention. The electron, a fermion, would have a partner called the selectron, a boson. The photon would have a partner called the photino, a fermion. Quarks would have squark partners. Neutrinos would have neutrino partners. These supersymmetric partners would be like quantum mechanical dance partners, forever linked by the deep symmetries that govern the universe. Even though we haven't seen them yet, their existence would solve many mathematical headaches and bring a profound balance to the equations of physics. But here is the puzzling part that has scratched the heads of physicists for decades. If every particle has a supersymmetric partner, a shadow twin just waiting to be found, where are they? We have looked. We have smashed particles together at incredible speeds. Yet, we have never observed a selectron, a photino, or any of the other predicted superpartners. The charts remain empty. The answer, according to supersymmetric theory, is that supersymmetry is broken in our current universe. This is a subtle concept. It does not mean the symmetry does not exist at a fundamental level. Rather, it means that the conditions of our current low-energy, cool universe hide the symmetry from direct observation. Think of it like looking at your reflection in a funhouse mirror, the kind you find at a carnival with curved glass. The fundamental symmetry between you and your reflection is still there. There is a one-to-one correspondence between your hand and the mirror hand, but the curved surface distorts the image. Your reflection might look shorter, fatter, or completely warped compared to the real you. In the very early universe, just fractions of a second after the Big Bang, when temperatures and energies were unimaginably high, supersymmetry might have been unbroken. It was a perfect mirror. Particles and their superpartners would have had identical masses and properties, existing side by side in equality. But as the universe cooled and expanded, something dramatic happened. A phase transition occurred, similar to water freezing into ice. This event broke the symmetry. It shattered the perfect mirror. In this new, colder state, the superpartners became much heavier than their ordinary counterparts. Because they were so heavy, they became unstable, decaying quickly into lighter, more familiar particles. This breaking of supersymmetry is actually essential for explaining why our universe looks the way it does. If supersymmetry were unbroken today, every electron in every atom would be accompanied by a selectron partner. The rules of chemistry would be rewritten. The universe would be a very different, chaotic place, possibly one where stable atoms, stars, and life as we know it could not exist. But even though supersymmetry appears to be broken and hidden in our low-energy world, it still plays a crucial role in the mathematics of string theory. In fact, string theory seems to require supersymmetry to work at all. Without it, the equations misbehave. The theory produces particles with negative mass squared, called tachyons. These are faster-than-light particles that would make the universe unstable and violate the basic laws of cause and effect. Supersymmetry fixes this. It also helps solve some of the deep technical problems that arise when trying to unify quantum mechanics with gravity. Remember the quantum foam, those violent fluctuations of space-time at the smallest scales? Supersymmetry tames them in the complex calculations of quantum physics. Fermion loops, matter loops, and boson loops, force loops, tend to have opposite mathematical signs. When supersymmetry is present, these two types of loops cancel each other out perfectly. It is like adding a positive number to a negative number of the same size, you get zero. The infinite, nonsensical results vanish, leaving behind finite, well-behaved predictions. There is something deeply beautiful about this idea. It suggests that the universe has an underlying balance, a cosmic yin and yang. Every type of particle is paired with its complementary opposite. Matter is balanced by force. The loners are balanced by the socialites. And the quantum fluctuations that could destroy reality are tamed by the presence of these shadow partners. However, beauty is not proof. Supersymmetry remains one of the great unconfirmed predictions of theoretical physics. Despite decades of searching in massive particle accelerators like the Large Hadron Collider, scientists have found no direct evidence for selectrons, photinos, or any other superpartners. This silence is deafening to some, but it does not necessarily mean supersymmetry is wrong. It suggests that if these partners exist, they must be much heavier than we anticipated, hiding just beyond the energy frontier of our most powerful machines. Some physicists remain optimistic, believing that as we build more powerful colliders, we will eventually smash through the energy barrier and reveal this hidden world. Others worry that supersymmetry might be broken so severely that the partners are too heavy to ever be produced in a laboratory. They might exist in principle, but remain forever beyond our experimental reach. There is also the intriguing possibility that supersymmetry is hiding in plain sight. We know that most of the mass in the universe is made of something called dark matter, invisible stuff that holds galaxies together with its gravity. We don't know what it is, but the lightest supersymmetric particle, if it exists and is stable, would be an ideal candidate for dark matter. It would be heavy, neutral, and interact very weakly with ordinary matter, making it invisible to telescopes but detectable through its gravitational pull. The missing partners might be the ghost-like glue holding our galaxy together. The mathematics of supersymmetry connects the geometry of space and time with the properties of quantum fields in ways that seem almost too elegant to be accidental. Whether this beauty reflects a deep truth about nature or is simply a seductive artifact of our own theoretical constructions remains one of the great open questions. As you settle into the quiet rhythms of approaching sleep, you might imagine this hidden mirror world. Imagine that for every atom in your body, every photon of light striking your eye, and every quantum field permeating the room, there is a shadow twin. They would be there, but not there. Real, but unobservable. Partners in a cosmic dance that maintains the balance and stability of reality itself. In the deepest mathematical sense, you would never be alone. You are always accompanied by your invisible supersymmetric shadow, a quantum reflection dancing through dimensions beyond perception. But if hidden dimensions and shadow particles aren't strange enough, string theory leads us to an idea that challenges the very nature of space itself. The strangest idea in string theory isn't about tiny strings or extra dimensions. It is the suggestion that everything you experience, the entire 3D world, might be a projection. Imagine you are looking at a hologram. You know, the kind those shimmery images on a credit card or a sci-fi display. It appears to be three-dimensional. You can move your head, and the image shifts perspective. You can see behind objects. It looks like it has depth and volume, yet you know that all the information creating this illusion is actually etched onto a flat, two-dimensional piece of plastic. Now, imagine something far more radical. What if the entire universe is like that? What if the room you are sitting in, the stars in the sky, and the depth of space itself are actually a projection from information encoded on a distant, two-dimensional surface? This isn't science fiction. It isn't a plot from a movie. It is one of the most serious and revolutionary ideas to emerge from modern physics, and it is called the holographic principle. The idea didn't start with string theory directly. It began with black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery about these mysterious objects. He found that the entropy of a black hole, which is essentially a measure of how much information it contains, is proportional not to its volume, but to its surface area. This was completely unexpected. Think about a library. The amount of information in a library depends on how many books you can fit inside the rooms, the volume. If you double the size of the room, you can fit twice as many books. But Bekenstein found that for black holes, the information seemed to be plastered on the walls. It was like finding that the capacity of a library depended only on the surface area of the bricks on the outside, not the space inside. Stephen Hawking's subsequent work deepened the mystery. He showed that black holes aren't truly black. They emit a faint glow of radiation. As they radiate, they slowly evaporate. But this led to a crisis. If a black hole disappears, what happens to the information of all the stuff that fell into it? Quantum mechanics says information can never be destroyed. This created the famous black hole information paradox. String theory offered a potential resolution through the holographic principle. The idea is that all the information that appears to be lost inside the three-dimensional volume of a black hole is actually safely preserved, encoded on its two-dimensional boundary, the event horizon. The three-dimensional interior is just a projection, a holographic reconstruction of the data stored on the shell. But the implications of this idea extend far beyond black holes. Physicists realized that if this principle works for black holes, why couldn't it apply to the entire universe? Perhaps all of three-dimensional space, everything you see, touch, and move through is actually a holographic projection. The source of this projection would be information encoded on a distant two-dimensional boundary, unimaginably far away at the edge of the observable universe. The information encoded there would contain a complete description of everything that happens inside the universe. Every particle interaction, every chemical reaction, every thought you think would be represented by data on this cosmic screen. What you experience as three-dimensional reality, the feeling of moving forward and backward, up and down, would be a kind of grand illusion. It is a sensory experience created from flat data. The mathematics of this holographic correspondence has been worked out in remarkable detail for certain simplified mathematical universes. Physicists have found exact dictionaries that translate physics in three-dimensional space into physics on a two-dimensional boundary. This correspondence is so precise that it has led to a completely new way of thinking about the fundamental nature of space and time. We used to think that space was the stage, and things happened inside it. The holographic principle suggests the opposite. It suggests that the 2D boundary is the fundamental reality. The 3D space we live in is emergent. It is a useful illusion, like the 3D world in a video game that is generated by a flat chip. Think of it like watching a movie in a cinema. The movie appears to take place in a deep, three-dimensional world. Characters run towards the camera or away from it, but the fundamental reality is just the flat screen and the pattern of light pixels. The 3D world of the movie is real in the sense that you experience it, but it is not fundamental. It is a projection. The holographic principle also offers new insights into the spooky nature of quantum entanglement, the connection between particles that Einstein found so troubling. In the holographic description, particles that appear to be far apart in the 3D interior might actually correspond to connected regions on the 2D boundary. The mysterious connection that seems to travel faster than light might simply be a reflection of the fact that on the fundamental 2D surface, those 2 points are right next to each other. There is something both unsettling and beautiful about this picture. It is unsettling because it suggests that your direct experience of space might be fundamentally illusory. The depth you feel so certain about is a projection, but it is beautiful because it reveals a deep unity. It shows that the same underlying information can manifest in radically different ways, as a flat code or as a rich, volumetric world. The holographic principle has also become a practical tool. The mathematical techniques developed to understand it have helped physicists solve problems in other areas, like understanding superconductors. The holographic dictionary allows them to translate impossibly hard problems in 3D physics into solvable problems in 2D physics. But perhaps the most profound implication is what it suggests about the nature of information itself. It hints that at the deepest level, the universe is not made of matter or energy, but of information, bits and bytes of cosmic data. If everything you experience is ultimately information encoded on a distant surface, then we arrive at a startling conclusion. Information is more fundamental than space, time, matter, or energy. Reality, in the deepest sense, would be informational rather than material. This view connects physics to some of the oldest and deepest questions in philosophy. What is consciousness? How does the subjective feeling of being you arise from objective physical processes? If reality is fundamentally information, then consciousness might be understood simply as a particular way that information processes and experiences itself. As you drift towards sleep, your consciousness gradually releasing its grip on three-dimensional experience, you might imagine yourself as both the projection and the projected. You are both the data encoded on some distant cosmic boundary and the vivid experience that emerges from that code. In dreams, the normal rules of space and time already become fluid. Perhaps sleep offers a glimpse of what reality might be like if we could step outside the holographic projection and see the universe from the perspective of the encoding boundary itself. However, we must pause here. As compelling as these ideas are, not everyone is convinced that the universe is made of strings or holograms. In fact, many scientists have some pretty good reasons for their doubts. String theory is undeniably beautiful. Its mathematics is elegant, and its unifying vision is compelling. But in science, beauty alone does not make a theory correct. Nature is under no obligation to be elegant by human standards. Because of this, string theory has attracted serious criticism from thoughtful physicists who question whether it deserves its status as the leading candidate for a theory of everything. The most fundamental criticism is simple, but devastating. String theory has yet to make a single testable prediction that distinguishes it from other theories. In the strict rules of science, theories are judged by their ability to make predictions that can be confirmed or contradicted by experiment. Take Einstein's general relativity. It made risky predictions: light bending around stars, clocks running slower in gravity, gravitational waves. Over the last century, every single one was confirmed. The theory put its neck on the line and survived. String theory, despite decades of development, has struggled to do the same. The energy scales where stringy effects would appear are so high that they existed only in the first moments after the Big Bang. The extra dimensions are supposedly so small that they are far beyond the reach of any microscope. The predicted supersymmetric particles remain stubbornly absent. Critics argue that without testable predictions, string theory isn't really a scientific theory in the traditional sense. It might be better described as a mathematical framework or a philosophy. It may be intellectually stimulating, but if it cannot be proven wrong by observation, does it truly belong in physics? Another major criticism involves the landscape problem. We know that different ways of folding the extra dimensions lead to different possible universes. The problem is that the number of possible ways to fold them is enormous, possibly infinite. Estimates suggest there might be 10 to the 500th power different stable configurations. This vast multiplicity makes it virtually impossible to extract specific predictions. If you ask string theory, what is the mass of an electron? The theory essentially answers, it can be almost anything, depending on which universe you are in. If almost any conceivable physics can be realized somewhere in the string landscape, then the theory doesn't really predict anything specific about our universe. It is like a theory that predicts the outcome of a coin flip by saying, somewhere in the multiverse, every possible sequence of heads and tails occurs. That statement might be true, but it doesn't help you predict whether the coin in your hand will land on heads. This issue creates what is called the naturalness problem. Physicists prefer theories where the observed numbers of nature emerge naturally from fundamental principles. But in string theory, getting a universe that looks like ours seems to require picking exactly the right configuration. Finding one specific grain of sand on all the beaches in the world, some string theorists argue that the anthropic principle is the answer. We live in this specific universe simply because it's the only kind that can support life. But critics find this unsatisfying, arguing that it gives up on the goal of scientific explanation. There are also sociological criticisms. Some argue that string theory has sucked the air out of the room because it dominates top universities. It captures the majority of funding and bright young minds, potentially neglecting other promising approaches to quantum gravity. Young physicists often feel pressured to work on string theory just to build a career. String theorists, of course, have strong responses. They point out that many successful theories started as purely mathematical frameworks that took decades to connect with experiment. They argue that the mathematical consistency of string theory is so restrictive that it is actually highly constrained. You can't just adjust the rules to fit the data. Moreover, they emphasize that even if it never becomes the final theory of everything, it has revolutionized pure mathematics and provided powerful tools for modeling fluids and materials. The debate reflects a deeper question about scientific progress. How long should we pursue a promising but unconfirmed path? At what point does mathematical beauty become insufficient? But let's say we do want to test it. How do you prove that invisible strings exist when they are smaller than anything we have ever measured? The challenge is a matter of scale. Testing string theory experimentally is like trying to study the brushstrokes of a painting hanging on the moon, using only your naked eye. The strings that might make up reality exist at the Planck scale. This is a realm of distance so tiny and energy so high that it defies comprehension. To put this in perspective, if you took a single atom and scaled it up to the size of our entire solar system, a string inside it would still be smaller than a human hair. To probe this scale directly, we would need to smash particles together with unimaginable force. The energy required to see a string would be about 1,000,000,000,000 times higher than what our most powerful machines can achieve. Building an accelerator capable of reaching such energies would require a machine larger than our entire galaxy. We would need to ring the Milky Way with magnets. Since we cannot build a galaxy-sized machine, physicists have to be creative. They look for indirect evidence, subtle signatures of stringy physics in the world we can observe. One promising avenue is the search for supersymmetry. As discussed, string theory predicts that every particle has a partner. If these superpartners exist and are light enough, they might be produced in our current colliders. For over a decade, detectors at CERN have sifted through collision debris looking for these particles. So far, the results have been silence. No evidence has emerged. This doesn't rule them out, but it pushes them into higher energy ranges we can't yet reach. Another approach involves testing gravity itself. In string theory, gravity corresponds to closed strings, which can leak into extra dimensions. If this happens, gravity might behave differently at very small scales. Scientists have performed incredibly delicate experiments to measure gravitational attraction between objects separated by fractions of a millimeter. So far, Einstein's gravity holds up perfectly. No leaks have been found. We also look for missing energy in particle collisions. If a graviton is created in a collision and flies off into an extra dimension, it would look like energy simply vanished from the experiment. While there have been some anomalies, nothing definitive has been seen yet. Finally, the study of black holes offers a potential testing ground. If string theory's description of black hole information is correct, it might make predictions about the radiation they emit. Since real black holes are too big and slow to test, physicists have developed analog black holes. These are systems created in the laboratory that mimic the mathematics of black holes. For example, they use sound waves moving through a fluid. If you pump a fluid faster than the speed of sound, sound waves trying to move upstream cannot escape. They are trapped behind a sonic horizon, just like light is trapped behind a black hole's event horizon. By studying these sonic black holes, researchers can observe phenomena that look very much like the radiation predicted by theory. While this doesn't prove string theory is true for the universe, it gives us a sandbox to test the concepts. It is a way to touch the impossible physics of the deep universe right here on Earth. While these analog black holes created in laboratories cannot test string theory directly, after all, they are made of sound and fluid, not space-time. They play a crucial role. They allow us to test the quantum mechanical principles that underlie string theory's approach to the universe. They prove that our mathematical descriptions of horizons and entropy are robust, even if we cannot yet touch the strings themselves. But if we want to find footprints of the strings, we must look up. Cosmology offers perhaps the most promising arena for testing these ideas. The extra dimensions, the vibrating strings, and the complex folding of space might have left subtle imprints on the cosmic microwave background radiation. This is the afterglow of the Big Bang, the oldest light in the universe, which we can observe with incredible precision. String theory makes predictions about the patterns of temperature fluctuations in this ancient light. It suggests that the violence of the early universe might have stretched microscopic quantum tremors into vast cosmic scars. Future observations might be able to read these signatures. The theory also predicts the existence of cosmic strings. These are not the tiny fundamental strings we have been discussing, but massive, extended objects that might have formed in the early universe. Imagine a crack in a block of ice, but extending across the entire cosmos. These cosmic strings would be unimaginably heavy and thin. If they exist, they would bend the light of distant galaxies in a very specific way, creating a gravitational lens that astronomers could detect. Down here on Earth, there is also the possibility of discovering stringy physics through the study of materials. Surprisingly, some of the mathematical techniques developed for string theory have found applications in understanding exotic phases of matter. Some materials exhibit behaviors that can be modeled using string-like objects, while a superconductor is not made of fundamental cosmic strings. The mathematics describing it is startlingly similar. This demonstrates that string-like physics can emerge in complex systems, giving us confidence that the mathematics is not just a fantasy. Perhaps most intriguingly, string theory has made deep connections to the study of quantum entanglement and information theory. The holographic principle, which we discussed, suggests a deep relationship between geometry and information. These relationships are currently being tested in laboratory experiments with quantum computers. While these experiments don't prove our universe is a hologram, they verify that the mathematical dictionary translating geometry into information is accurate. The challenge of testing string theory has also driven massive advances in pure mathematics. Researchers have had to invent new ways to calculate physical processes and understand the geometry of extra dimensions. Even if string theory ultimately proves to be incorrect as a theory of everything, these tools will remain. They have found applications throughout physics, from nuclear interactions to fluid dynamics. The toolbox is valuable, even if the house it was built to construct is never finished. This situation has led to a divide in the scientific community. Some physicists argue that the traditional notion of experimental testing may not apply to string theory in the same way it applies to simpler theories. They suggest that string theory might be better understood as a framework, a language that unifies and organizes our understanding of physics, rather than a conventional theory that predicts the reading on a dial. Others stand their ground. They maintain that without experimental confirmation, string theory remains speculative, no matter how beautiful its mathematics might be. They argue that physics is, ultimately, an empirical science. It is the study of what is, not just what could be. A theory must eventually make contact with observation to be considered scientifically valid. The search continues, driven by both the desire to test our most sophisticated ideas and the hope that such evidence might reveal new physics beyond our current understanding. As you drift towards sleep, imagine the scientists working through the night in laboratories around the world. Imagine them sifting through petabytes of data from particle collisions, searching for subtle clues that might reveal whether the universe really is made of music, whether reality really does emerge from the vibrations of invisible strings dancing through hidden dimensions. But why do they persist? Why do thousands of brilliant minds dedicate their lives to a theory that cannot be tested yet? The answer often comes down to one word: beauty. Sometimes, the most beautiful mathematical equations describe truths about the universe that we discover long before we understand them. There is something mysteriously compelling about mathematical beauty in physics. It is a quality that is hard to define, but impossible to ignore when you encounter it. Physicists often talk about elegant equations and beautiful symmetries. String theory is perhaps the ultimate example of this phenomenon. It is a framework so mathematically rich, so intricate, and so perfectly balanced that many practitioners are drawn to it as much by its beauty as by its potential to explain the universe. But what does it mean for mathematics to be beautiful? And should we trust our aesthetic sense when it comes to understanding reality? In physics, mathematical beauty often manifests as simplicity emerging from complexity. Think of Einstein's famous equation, E equals mc squared. It is beautiful, partly because it expresses a profound connection between two seemingly different things, matter and energy, in just a few symbols. The equation seems almost too simple to contain such deep truth, yet its implications revolutionized our understanding of reality. String theory exhibits a different kind of beauty, the beauty of unification. The theory doesn't just describe particles or forces or space-time geometry in isolation. Instead, it weaves all of these phenomena together into a single structure where each element supports and constrains all the others. You cannot just add a new feature to string theory arbitrarily. The math will reject it. It is like a vast, intricate musical composition where every note is related to every other note. If you change one bar, the whole symphony falls apart. The mathematical structures that appear in string theory often seem to have lives of their own. They reveal unexpected connections that their creators never anticipated. Take the Calabi-Yau manifolds, those six-dimensional shapes we visualized earlier. They were studied by mathematicians for decades before anyone thought they might be relevant to physics. Then, physicists working on string theory discovered something called mirror symmetry. They found that two completely different Calabi-Yau shapes could give rise to the exact same physics. This was a shock to pure mathematicians. It revealed deep truths about geometry that they had never suspected. This interplay between physics and mathematics has been one of string theory's most remarkable contributions. The theory has led to advances in geometry and topology that might never have been discovered through pure math alone. The holographic principle also exemplifies this beauty. The idea that physics in a 3D volume can be perfectly described by a theory on a 2D boundary represents a deep duality. These dualities are perhaps string theory's most beautiful feature. The theory predicts that what appears to be one kind of physics from one perspective might appear to be completely different physics from another. Yet, both descriptions are equally valid. It is as if the same symphony could be heard as a waltz by one listener and as a tango by another. Both interpretations sound completely different, yet both are accurate representations of the same underlying musical structure. This suggests that reality is richer and more flexible than we ever imagined. But we must be careful. The relationship between mathematical beauty and physical truth is complex and sometimes misleading. History is filled with beautiful mathematical theories that turned out to have no connection to reality. Just because a theory is elegant doesn't mean nature uses it. Conversely, there are physical theories that work perfectly, but seem mathematically ugly. The standard model of particle physics, our current best description of the subatomic world, is notoriously messy. It requires us to plug in many arbitrary numbers by hand. It lacks the unifying elegance of string theory, and yet it works. It agrees with every experiment we throw at it. This raises a profound question. Is mathematical beauty a reliable guide to truth, or is it simply a human preference? Some physicists argue that the universe is under no obligation to conform to our aesthetic tastes. Nature might be fundamentally messy. Our search for elegant theories might reflect our own psychological need for order, rather than the objective features of reality. Others maintain that mathematical beauty is a reliable indicator. They point to the unreasonable effectiveness of mathematics. Mathematics is a human creation, developed to count sheep or measure land. Yet, abstract mathematical structures often turn out to describe physical phenomena with uncanny accuracy. It is as if the universe is written in a mathematical language that we are slowly learning to read. String theory represents the extreme test of this principle. The theory is evaluated primarily on its aesthetic and mathematical consistency because experiments are so hard to do. If string theory is correct, it will be a triumph of beauty as a guide to truth. If it is wrong, it might teach us that beauty alone is not enough. There is also the question of whether this beauty reflects something objective about the universe or something subjective about the human mind. Perhaps we find certain structures beautiful because our brains evolved to detect patterns, or perhaps our minds are attuned to the deep structure of the cosmos because we are part of it. The beauty of string theory has certainly influenced the direction of physics for 50 years. It has attracted the most talented minds and built the most impressive mathematical cathedrals, but it has also led to criticism that the field has become too focused on aesthetics at the expense of reality. As you settle into the gentle rhythms of approaching sleep, reflect on this deep mystery. Whether string theory ultimately proves to be the final description of nature or not, it has revealed structures of extraordinary richness. These structures exist in the realm of human thought and imagination, but they might also describe the fundamental architecture of reality itself. In the space between waking and sleeping, between the mathematical and the physical, we arrive at the deepest question of all. Is the universe really made of music? And if so, are we finally learning to hear its song? After wandering through dimensions both hidden and vast, after contemplating vibrating strings, holographic projections, and infinite multiverses, we must ask, what would it actually mean for you if string theory is correct? How would this change your understanding of who you are and what it means to exist? If string theory is right, then the most basic fact about reality is that it is musical. Every particle, every force, every field, every bit of matter and energy in the universe would be nothing more than different vibrations of the same fundamental strings. The electron in every atom of your body, the photons carrying the light you see, and the gravity that keeps you resting in your bed would all be different notes in the same cosmic symphony. This musical nature of reality implies that the apparent diversity of the world is actually a kind of illusion. At the deepest level, everything is the same thing, just vibrating in different ways. It is as if the entire universe were a vast orchestra, where every instrument from the tiniest piccolo to the deepest drum is actually the same fundamental instrument, just played with a different touch. The implications of this unity are profound. It would mean that you are literally connected to everything else in the universe at the most basic level possible. The strings that make up your thoughts would be the exact same kind of strings that make up distant stars, swirling black holes, and drifting galaxies. When you look up at the night sky, you wouldn't be looking at something foreign and separate. You would be looking at different expressions of the same underlying musical reality that you, yourself, are made of. String theory also suggests that space and time, the very arena in which your life takes place, might not be fundamental features of reality. Instead, they might be emergent properties. Think of the smooth surface of a lake. To us, it looks like a continuous sheet, but we know it emerges from the complex interactions of countless individual water molecules. In the same way, the space-time you move through might emerge from the interactions of vibrating strings in higher dimensional space. This suggests that the categories we use to organize our lives, past and future, here and there, cause and effect might be approximate descriptions. They work well in everyday life, but they break down when you probe the deepest levels of reality. At the string scale, the familiar distinctions between space and time, between self and other, might dissolve into something far more unified. The holographic principle carries this interconnectedness even further. If reality is truly holographic, then every part of the universe would contain information about every other part. It is like a shattered mirror where each fragment still reflects the whole room. This would mean that, in some deep sense, you already contain information about everything that exists. The boundaries between inside and outside, between the observer and the observed, would be revealed as useful illusions rather than solid walls. String theory's prediction of extra dimensions also radically expands our conception of what exists. If there are indeed 6 extra dimensions folded up at every point in space, then reality is far richer than our senses can detect. You would be moving through these extra dimensions all the time without knowing it. You would be like an ant crawling on the surface of a vast, intricate sculpture, completely unaware of the complex 3-dimensional curves that surround its simple path. And then there is the multiverse. If string theory is correct, what you think of as the universe might be just one bubble in an infinite foam of realities. Each bubble could have its own laws of physics, its own particles, and its own story. Every possibility that can exist mathematically might exist somewhere in this vast landscape. This would mean that every choice not made, every path not taken in our universe is actually realized somewhere else. From this perspective, the question isn't whether other realities exist, but whether we can ever hear their distinct melodies. You would be traveling in your own branch of the multiverse, able to contemplate the infinite garden of possibilities, even if you cannot visit the other flowers. Perhaps the most profound implication of all is what string theory suggests about consciousness. If the holographic principle is correct, reality might be better understood as information processing a cosmic computation. If reality is fundamentally informational, then consciousness might not be something separate from the physical world. Instead, it might be a particular way that the universe processes and experiences information about itself. You might be, in the most literal sense, the universe becoming conscious of itself. You are a temporary pattern in the cosmic music, a brief but beautiful theme in the infinite symphony of existence. Your thoughts, your dreams, and your sense of being a unique individual are real, but they are also expressions of something far larger. String theory does not answer the ultimate question of why there is something rather than nothing, but it does suggest that reality is far stranger, far more unified, and far more beautiful than we ever dared to imagine. And so, we find ourselves at the end of our gentle journey through the possibility that everything is music. We have wandered through dimensions, both hidden and vast. We have listened for the cosmic symphony that might be playing at the heart of every atom. Whether string theory is the final answer, or simply humanity's most beautiful attempt to understand the cosmos, it reminds us of a simple truth. We are part of a whole. Every breath you take, every heartbeat, every thought drifting through your mind as you settle into sleep. If the strings are real, they are all part of the same magnificent song. We have seen how the smallest vibrations might create the largest structures. We have contemplated mirror worlds, holographic projections, and infinite gardens of possibility. Through it all, the theory offers us a vision of profound unity. If this is true, you are woven into the fabric of the stars. Tonight, as your own vibrations slow and settle into the rhythm of rest, perhaps you will carry with you a sense of wonder for the hidden music that might be playing all around us. The strings too small to see, the dimensions too folded to touch, the symphony too vast to hear all of it weaving together the fabric of everything that is. Whether we live in a universe of vibrating strings or not, the search for understanding has led us to a place of beauty. It reminds us that reality might be fundamentally musical, fundamentally mathematical, and fundamentally interconnected in ways that transcend our everyday experience. And if you found any peace in this quiet exploration, if the possibility of cosmic music helps you drift toward your dreams, we would be honored to have you with us again. Thank you for joining us here at Fall Asleep with Science. Sleep well, and may your dreams be filled with the music of the spheres.